Good morning, one and all. Subject name compiler design. In this subject, today we are going to discuss about small description about parse trees and derivations, and also ambiguity which arises in parse trees. After that, how to eliminate ambiguity in parse trees if arises. So that is the course outcome, and we are going to learn this concept of both parse trees and ambiguitiness. Now, parse tree, it is nothing but it is a graphical representation of derivations. So we are going to write several derivations for a corresponding grammars, given grammars. So in this one, we are going to choose a particular derivation. What depends on the given string. So generally it will start by the root node, that is yes. So in the derivation tree, anyhow we are going to start with this start symbol that is called as yes, and the given input string based on. And the interior nodes, generally it is represented by non-terminals. Interior nodes in the given graph. And also leaf nodes, that is terminals, as described, that is epsilon or term t. A node can have any number of children such as x1, x2, so on, xn. Suppose if a rule A derives x1, x2, so on, xn exists. So that is going to be see this in this diagram. The root node here in this one, that is E derives E star E. E derives E star E. In this derivation, the start node, that is, it is to be considered as a root node. It is to be considered as root nodes. And terminals are leaf nodes, whereas non-terminal nodes are interior nodes. So here, in this case, we are going to describe once again with let us take an example of the derivations such as E derives E star E, E derives E plus E star E, E plus E, E derives E star E, and E derives ID. These are the derivations. We are going to derive a string. In this derivation tree, E derives E star E. E derives, and left child, one of the child is E and another one is, that is capital E, then star followed by right children, that is capital. So in this way we are going to describe a parse tree notation. So here the first E corresponds to any of the derivation which is applied. So let us say consider this E plus E is the derivation. So E, that is leftmost, that is here, we are going to consider this one as E plus E. So as part of E derives E plus E, we are going to construct a new parse tree diagram based on the previous one. So here in this case, for example, E derives E star E, this portion is to be considered kept as it is in the similar way of previous diagram. But the portion that is belongs to this E derives E plus E can be now derived from the previous because of the applied derivation. From this, the derivation, if you observe, from this previous derivation, the next parse tree that is to be generated with the help of one more derivation. So here, any possibility of applying a derivation, that is, for example, here E plus E star E. So here once again the non-terminal E can be evaluated either in terms of E plus E or E star E or E. So based on the string, input string, we are going to verify the E is to be substituted with this as E derives ID. E derives ID. and then we are going to write E star E, that is ID plus E as one part of E, and then this E is kept as it is. In the next derivation of the generation of the parse tree, we are going to apply this derivation, same derivation, in terms of this E derives ID once again, and we are going to get a new derivation tree. And finally, the last non-terminal E also substituted with this one, that is E derives ID, and we are going to a new parse tree derivation. So here in this derivation, the last non-terminal, that is to be here ID, and then move to plus, and then move to ID leaf nodes, and then ID, and then star. From ID it goes to the star, and then it goes to the ID. So what is the here ID, and this is plus. So this is ID, and this is star, and this node is ID. So the final string that is derived from the parse tree is ID plus ID star ID. ID plus ID star ID. So in this way, we are going to generate parse trees for the given derivations. Let us take one more, that is notation, that is, for example, a parse tree can be represented with previous notation which you have generated finally, ID plus ID star ID. So that is lower. So in this diagram, all the leaf nodes that is to be represented as terminals. That is, for example, ID is a terminal plus ID star is to be considered. All leaf nodes to be considered. Whereas interior nodes can be considered as non-terminal. So in this parse tree, so here capital E, interior node, all these interior nodes are to be considered as non-terminals. Whereas leaf nodes are to be considered, that is ID plus ID plus star, all these to be considered that is as leaf nodes. And the in-order travels gives the original input string. All the leaves of a parse tree, when read left to right, are called as frontier or yield of a tree. Whenever we are going to read all the symbols inside the parse tree, that means level by level. That means, see here, last leaf node here ID, here plus, here ID. So whenever you read all this one from left to right, so that is to be described in terms of a yields of a tree also. Here we are going to apply some associativity and precedence of the parse trees, and whenever you traverse the operator that gets higher and one is lower, so based on the parent and child relationship also we can observe. So we are going to see how ambiguity arises in this parse trees. Previously we have taken one defined grammar, and with help of grammar we are going to derive the string and generated a parse tree. So here ambiguity arises with the help of this parse tree. Why? Because the grammar is said to be ambiguous. The given grammar is said to be ambiguous based on the graphical representation of parse tree. Generally, we are going to develop a parse tree for the given string with the help of the given grammar. And if the given grammar has leftmost derivation or rightmost derivation, we are going to apply leftmost derivation and rightmost derivation more than one for the same parse tree. Ambiguity arises when it is having more than one leftmost derivation and more than for the same string. So then we can say that the grammar is said to be ambiguous. Otherwise, if the derivation tree doesn't contain more than one leftmost derivation and more than one rightmost derivation, then we can say that the grammar is unambiguous. Where ambiguity arises if there is more than one derivation, leftmost or rightmost, for the same string. For the same string, it is obtained, then we can say that it is ambiguous. Else, it is not ambiguous. It is not ambiguous means unambiguous. So, for example, we are going to consider a given grammar, that is S derives ASB. So, here more than one leftmost derivation. Here S derives small a, capital S, small b. Another derivation S derives capital S, capital S. Third derivation S derives epsilon. So these are the productions which are given. In these rules, we can take any of the production for the development of parse tree. So, for example, if you take S derives A, S, B, that means small a, capital S, capital B. Then we derived with a root node capital S and a small a, capital S, small b. Once again, this yes may have the choice of opting either this derivation or second derivation or third. So, for example, let us say if you take the derivation the same, that is ASB, so small a, capital S, small b, and then we applied S derives epsilon as third derivation. Then the string that is derived here, small a, epsilon, small b, small b. So A, B, B. Epsilon into A is A only. So that's why A epsilon A, B, B. So that's why you get one string. The same string, it is derived with the help of another derivation also. That is leftmost derivation also. In the previous sessions, we discussed about this leftmost, how to evaluate left and rightmost derivations. See the video once again how to evaluate this left and rightmost derivations. And here we are concentrating mainly on the construction of parse tree with the help of that is leftmost and rightmost derivations. See, for example, here let us say here we are going to take S derives a second one, that is a derivation, that is rule, second rule that is applied capital S and on capital S. Then we may take either the option that is S derives epsilon. Then the second S to be derived with the help of ASB. That will be small a, capital S. Once again, this capital S may derived with the help of that is this row production rule, small a, capital S, B. Once again, capital S, epsilon. Once again, capital S, epsilon. So in this case, we are going to get this epsilon A, small a, epsilon B, small. So what is that? We are getting AAB. So what is the string that is defined for this diagram and what is the string that is defined for this diagram? Both are same, but this is possible with one leftmost derivation, and this is also possible with one more leftmost derivation. So many leftmost derivations may exist. So this we can say that the grammar is ambiguous. Grammar is said to be ambiguous. Why? Because it contains more than one leftmost and rightmost, or more than one leftmost. So if at all, if possible, we can also look into this rightmost also. Why? Because it may exist. So one of them is proved, that is either left or right, then ambiguity arises. So no need to check the second one also. If any one, either left or rightmost. So in this example, leftmost derivation exists with the two cases for the same string. defined string AA. So that based on the processing of this AA only, we are going to implement this derivation. So we have taken a new, that is A capital B. So based on this, we have taken a production, this one initially. And next derivation we have taken as S derives ASB. Why? Because second A is to be required. So this ASB. And in the third derivation, we applied S derives epsilon. So we are getting a string A double B. Here in this case, yes, we applied with S derives capital S as a second rule. We can take any of them of the production rule. So based on this, we applied S derives epsilon as the third rule. And in the second, we have applied this as A small capital S B. And in the third, that is the left, that is capital S, here in this case capital S, here capital S, ASB. And in this case, epsilon AA, S derives epsilon as this rule. So we applied epsilon B. That means here S epsilon ASB. That is S derives A epsilon B. So S derives A epsilon B. This is the portion which S derives ASB. S derives ASB. So in the second part A, S derives epsilon B. So B. So that is S derives epsilon. So in this case, we are going to write A derives, S derives small a, capital S, B, capital S. So this portion. And next derivation, A capital derives epsilon, B, S derives epsilon. So we are going to describe notations such as leftmost derivations with the help of the given input. We are going to verify the string based on the input string only. We are going to apply this type of notations, and we can say that ambiguousness. Let us take one more example. E derives whether this grammar is ambiguous or not, we are going to prove, and the string that is to be given as ID plus ID star ID. String that is to be given as ID plus ID star ID. So in this example, we can first take a description of parse tree. First implementation, that is E derives E plus E as a first rule. And second rule is E derives E star E. And third rule, E derives ID. So as this one we applied E derives E plus E. And then first E, that is E derives E plus E. And the first E we implemented, that is E derives ID, that is leftmost derivation. And then next E, that is to be with E star E. E star E. And then the leftmost, that is ID star E. And then ID plus ID star the rightmost, that is not E, that is ID. So what is the string? That is same string we achieved. Same string we achieved. That is the leftmost derivation with the help of the given grammar. E derives E plus E, E derives E star E, and E derives ID. So we applied E star E as the second rule and E derives ID as the third. So second one, first one. So let us take the same grammar, given grammar, with the help of another notation, that is, for example, parse tree only. But here now, let us say, if I take the derivation, that is E star E, at the leftmost, that is the, this time we have taken the second rule, E star E. And then E, then let us say capital E derives E plus E. That is first. E plus E. Then capital E derives, that is the second. Then the first E derives ID, then second derives ID star, then E derives ID. So the same string that is to be generated, ID plus ID star ID. So here we can say that a grammar, for the given grammar, two leftmost derivations are exist. Then we can say that the grammar is ambiguous. We can say that the grammar is ambiguous, and it is not ambiguous when there is no leftmost derivation exist more than one. Then we can say that it is not ambiguous. But here the grammar exists. Here derivations are exist for the same string. So in this, for this string it exists. So in this case we are going to say that no need to check the rightmost derivation. If leftmost doesn't exist, two cases, then we can go for rightmost. If already leftmost is to be proven with the two derivations, then we can easily say that ambiguousness exists. If not possible, then we can go verification with the rightmost derivation also. Whether it is rightmost is more than one applied or not, but here it is proved in the leftmost itself. So that's why we are not going to concentrate on once again with the rightmost. So leftmost itself, it is either leftmost or rightmost, then ambiguity arises. So these are the two leftmost derivations that is to be possible. These are the two parse trees that is to be generated for the given grammar, and hence the given grammar is ambiguous for the given string ID plus ID star ID. This type of grammar should be avoided. Why? Because the compiler does not know what is the parse tree that is to be taken while implementing this type of phases in the construction of parse tree, while implementing syntax analysis and semantic analysis phase. These problems arises. So this type of grammar is to be avoided. That means here, if we do not avoid, we do not know what is the parsing, unique parsing. So that is the first known, and we are going to verify evaluation of the corresponding expression. Is it clearly defined or not based on the given grammar? So if that is defined clearly, then the parse tree construction makes simpler and also avoidance of ambiguity. If the grammar is ambiguity, then compiler construction is to be very difficult, and it is not good for the source code generation. That is machine code generation from the source code. So there is no method can be used to detect automatically and remove. So we have to rewrite the entire whole grammar without ambiguity. So this is the possibility of occurrence we are going to write. For example, consider the following grammar and show that it is ambiguous grammar. So here in this given grammar, a grammar left hand side, that is statement equal to if expression then statement. That is one, and second one is that is if expression then statement else statement. So there will be two statements. One is yes if expression, that is expression E then statement, and second one is if expression then statement else statement. So for these two statements, ambiguousness exists to be verified. So for example, if you consider here, first statement, S statement is to be considered as if expression then statement. So if expression E1 then statement. So here statement is STF. So this is to be considered as first part, that is derivation of the parse tree. And if possible, you apply this any. So here there is no derivation for if, and here if there is no derivation. But here statement contains a derivation. So the statement derivation may apply either first one or second one. So already first one is applied. So if I apply this second derivation, that is if expression S1 else S2. If expression, that is the this step. If we apply this if expression, then statement. So this is one statement. So this total statement, either this one or this one. So here in this one it contains a statement. So that's why we applied one more statement. We, as a chance of this one, we are going to apply one more derivation, that is for the leftmost derivation exist or not. So in this case, see the second diagram. If you look at us, let us say statement to be applied as a second one. So this is the part which we applied. That means if expression, statement, else, statement. And for this scenario, we can apply a statement as one more scenario. So that is to be considered as this one, that is if expression. So if expression, then statement. So here the true positives are to be generated differently. Here we are going to consider these two positives to be translated differently with the else part. So else part is statement to here else part, but statement contains if else. So there is a inner if should be attached to the outer part. So ambiguous grammars. For example, here in this derivations, E derives E plus E, E minus E, E star E divided by E. So for this, we can apply, if any ambiguity arises, we can apply what? Precedence and associativity of operators to evaluate the expressions. So first, precedence of the operators are evaluated first, and these are, we know that precedency can be applied based on the associativity left to right or right to left. And how it is handle of precedence of operators. So we are going to divide the operators into groups of equal precedence. First one. And in each precedence level, introduce a non-terminal grammar rules, each of which represent expressions that share a binding strength. So the strength automatically depends on based on the level of associativity. So for the given group, we are going to see an example. And associativity of operators are also applied. That means either left to right, right to left, based on the given grammar. A factor is an expression that cannot be broken. Adjacent operators, either star or plus. So some here identifiers, parenthesis expressions. Identifiers are not possible to separate the letters of an identifier by attaching. That means with the operators we cannot split into them. That is, identifier split is not possible with this by attaching an operator. And expression parenthesis. That means any expression is with parenthesized. Then that means that is inside a parenthesis. It is used to prevent the operand of an operator outside of the parenthesis. That is indicates that the parenthesis. So here these two derivations, f derives id, f derives num. So here the expression is to be specified inside a parenthesis notation. So outside parenthesis it can protect. That means operators, any operands are to be avoidable. That is to be considered within the parenthesis. So that's why parenthesized expression is required. And identifier which to be described is the separation of the letters from the operator, any operator. So this is the notations to be used for elimination of ambiguity of an expressions. So here the term T is an expression which cannot be broken by an operator, that is plus, minus operators, and term A star B can be broken with the help of associative, that is either left or right. That means A star B means, that means either parenthesis is applied if more than one star. For example, here A1 star A star EB. Then if we apply the parenthesis, then we can remove this ambiguity, which one is to be considered. That means either A1 star A or A star B. So based on the associative parenthesis of the expressions, we can simply break down the expression into different parts, and we can apply the associative left to right or left to right to left. However, this placing an additive term such as A1 plus A star B. Suppose here in this case, so the precedence of the operator comes. That means which one is higher and which one is lower. Plus is to be considered and star. So based on this, the associative precedence, we can apply the star operation as the first. That means we give parenthesis A star B and then remaining part plus A1. So in this case, if the similar operators exist, then associativity appears left to right or right to left. If more than higher levels of precedence occurs, then we can apply the precedence, that is star, as a higher notation compared to the plus and star. If any other operator exists, then we consider the level of precedence and then automatically applied, and then based on this associativity parenthesis is of an expression to be evaluated. So this with the help of, we are going to avoid some ambiguity in the given parenthesis. See for example here T star F in the given expression, T star F, T divided by F, F. So here star and slash. So based on the precedence, either star to be considered or slash to be considered. So that way we are going to use the derivation trees in the construction of parse trees to avoid ambiguity. So for example, ambiguous grammar. It is there. It is the one which is contains. We know ambiguity and ambiguity. So this grammar is ambiguous. That is E plus T, E minus T, T star F, T derives T slash F, F derives ID. Now, so this type of grammar where the ambiguity arises to be eliminated with the help of a derivation tree, a parse tree, that is E derives. So this three derivations. E derives E plus T. So this E derives E plus T. And E derives T. T derives F, F derives ID. So here the final string is ID plus ID star ID. So in order to derive the string, we have eliminated the ambiguity with the help of the given derivations. So we applied a different rules with the help of this parse tree construction. Here T derives T star F. T derives F, F derives ID, F derives ID. So what is we get? ID plus this, and then we move to plus, and then leaf node ID, and then star, and then ID. So ID plus ID star ID. So there is no other parse tree which applied leftmost derivation and getting the same derivation with the help of these derivations. Same tree, same parse tree. That is a same string with the help of the derivation. Same string means ID plus ID star ID. So what we applied here, E derives first E plus T, then capital E derives capital T, and capital T derives capital F, and capital F derives ID. And the next derivation we applied T derives T star F, and T star F, T derives F, and F derives, and now, and here we applied ID plus T star F, where T derives T star F, and T derives F, and F derives ID, and then ID F derives ID. So the final string is ID plus ID star ID. So the based on the previous derivations only, that means E derives T, T derives F, F derives ID, and T derives T star F, and T derives F, T derives F, F derives ID, and so previous that is these are the production rules which are supplied for the given string generation of the parse tree. So here we are going to eliminate ambiguity by considering different rules with the associative and applied the um, level of precedence and parenthesis of expression, so that we can get rid of this ambiguousness. So here one more example, that is if at all if the derivations which exist with the statements such as if condition and if then else, then we are going to mark it as a statement notation, that is else with closed of if statement. So in those statements, if you want to eliminate ambiguity, then we are going to write a statement notation such as, see for example here, a match statement, and match statement is to be placed in between the elements. So here there will be two cases, one is match statement and one is unmatched statement. To eliminate ambiguity, match statement means here if then else statement containing no matched statements, and a statement which is not an if then else statement and not an if then statement. Whereas unmatched statement is an if then statement with no else part, and if then else statement where unmatched statements are allowed in else part but not in then part. But let us see with the help of an example. See here in this example, the statement is to be considered match statement or unmatched statement. So previous example we get this ambiguity. The match statement contains if expression then match statement, else matched. Whereas unmatched statement, if expression then statement, that is one, and if match statement else unmatched statement. So that is to be written with the help of construction of parse tree. So we have considered the two cases, matched and unmatched statement. So previous example, statement equal to if expression then statement. Again statement if expression match statement else match statement. Here match statement equal to, that is here we consider if expression then match statement. This is to be considered, and this is to be. If expression to match statement else match statement. So match statement may be this one. So we can eliminate this ambiguity by putting these matched and unmatched statements in the production rules. We can eliminate this production's ambiguousness with the help of this matched and unmatched statement. So that is to be considered with the help of this derivations such as matched and unmatched statements in the given if condition and if then else statements. So here we applied various associative and precedence rules, and first we have First, we have derived with the help of various trees, that is, we constructed parse trees, and then applied associativity precedence, and then we eliminated this ambiguities. So, in today's class, we described about construction of parse tree. Here, parse tree to be determined with the help of a root node, and then with the help of root node and leaf nodes and terminal nodes, that is, leaf nodes are to be represented with the terminals and non-terminals as the internal nodes, and we are going to give the brief description about a parse tree notations with the help of derivations. And if at all, if more than one derivation exists, then the corresponding parse tree, then we can say that it is a ambiguity arises. So that is said to be ambiguous. If not, it is not an ambiguous. So this parse tree we have taken with an example. So in this example, we have seen two leftmost derivations, and also second example, E derives E plus E, E derives E star E, E derives ID, where two leftmost derivations are exist for the given string ID plus ID star ID. So where the ambiguity arises, we are going to eliminate that one. To eliminate, we have to use some type of precedent. So here also the ambiguity arises if the expression. So for this, we are going to apply a statement with this notation, either matched statement and unmatched statements, to eliminate ambiguity with these two cases, with the elimination of ambiguity by applying a matched statement and unmatched statement. Then the associativity and precedence is applied with the help of this given grammar, that is, E derives E plus E, and we applied associativity, and based on this associativity and precedence, we can remove ambiguity easily. That is in this expression. So here we applied various precedents and parentheses and identifier F derives ID, F derives number, and F derives expression. So we are going to apply this type of associativity and then precedence levels, and then we get rid of ambiguity. Ambiguity are to be eliminated by applying this expression. So in this, we are going to get E derives E plus T, and E derives T, and T derives F, F derives ID. This part, E derives T, and T derives F, F derives ID. So this, in this case, no leftmost derivation exists for this same string. So here the leftmost is ID, and then plus, and then ID, and then move to the node, that is star, and then leaf node, that is ID. So the given expression is that is the given string ID plus ID star ID can be obtained with by applying the associated precedence and eliminate ambiguity. And we have also seen the expression notation, that is if statement, if then else. Then we have, by applying matched statement and unmatched statements, and we get rid of the solution, that is unambiguousness also. That is elimination of ambiguity in the case of else in if statements. So a distinguished match statement and unmatched statement is to be written. A match statement is to be written with the help of, that is, if else statement containing no match statements, whereas statement which is not an if then statement and not a if then statement. Whereas second, unmatched statement, that can be an if statement with no else part, whereas if then else statement where unmatched statements are allowed in the else part but not in the then part. So that is to be written as a derivation steps with containing two statements, that is three statements, statement, match statement, and unmatched statement. So in as part of this, we are going to construct the parse tree, which is to be eliminated the ambiguityness of else part in if. So in this way, we are going to describe the construction of parse trees and derivations ambiguousness removal, and then various types of laws associating precedents in the construction of parses. So these are the topics which are to be available from the given textbook, that is compilers principles, that is Horsity and Willman. So we'll come with the next topic, a new topic from the same subject, compiler design. And thanks you once again, all of you. Thank you for the given valuable time for giving this opportunity. Thank you very much. Once again, we'll come with next. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.